Welcome to How to Graph Rational Functions. This video will be a summary and a set of steps on how to graph them. So let's begin.
The first thing you should do, find x-intercepts. If you don't remember how to find x-intercepts, you can look it up in your notes, or I'll tell you now. X-intercept means where does the function cross the x-axis. If it crosses the x-axis, that's when y equals 0. So we set y equal to 0 and solve for x. Okay, but in this chapter, since everything looks like a fraction, we decided that you can actually set the numerator equal to 0. Solve for x. Same thing will happen whether you set y equal to 0 or the if the same thing doesn't happen, that means you did it wrong. So for example, if I have y equals 3x minus 6 over x plus 2, okay, that means that I set the numerator equal to 0. That's the numerator. 3x minus 6 equals 0, so x equals 2. Now remember, this is not how our answer should look. If I say what's the x-intercept, you tell me it is 2, 0, because it's a point, it's a coordinate. Okay? Next thing you have to do is find y-intercepts. Obviously you can do them in a different order, but this is just the way we kind of do it. Okay, so y-intercepts, same idea, except that it's when it hits the y-axis. Hitting the y-axis means x is 0, so we set x equal to 0. Solve for y. The nice thing is, you're just plugging in 0, okay, in for x, and so it's really easy to solve. Y equals 3x minus 6 over x plus 2. If this becomes a 0, and this becomes a 0, I've got 0 minus 6 over 2, negative 3. Again, this is not the final answer. You have to write it as 0, negative 3. So far for this graph, I already know I've got 0, negative 3 and 2, 0. I've got 2 coordinates on my graph already. Okay, but obviously there's more we have to do. The third thing we want, let's do some vertical asymptotes. Now if you don't remember, vertical asymptotes mean where the graph doesn't exist. Okay? And because rational functions have the property that you can't simplify or cancel anything, the way we always have vertical asymptotes is if we set the denominator equal to 0 and solve for x. So if you're looking at the example from before, 3x minus 6 over x plus 2, we set the denominator equal to 0, solve for x equals negative 2. The nice thing about vertical asymptotes, that is your final answer. Because x equals negative 2 means the vertical line that goes through x equals negative 2. So now, this is the information we know. But we still need horizontal asymptotes.
A horizontal asymptote shows the end behavior of a graph. Meaning, as x goes to infinity or positive infinity, what's happening to the ends of the graph? Or where do they approach? One thing to keep in mind that differs horizontal asymptotes and vertical asymptotes is that with a horizontal asymptote, the graph can cross the asymptote. It is allowed to cross it. The only thing is, at the ends, it approaches. So there are graphs, certain graphs that look like this, where it crosses in the middle, but then continues approaching the horizontal asymptotes at the end. This part is totally fine. When we have a rational expression that looks like ax to the n plus ... divided by bx to the m plus ... then we have some very important and specific rules in order to find horizontal asymptotes. So with the rational expression or rational function ax to the n plus some other stuff over bx to the m plus some other stuff. The degree of the numerator, meaning the largest exponent in the numerator, is n, and the degree of the denominator, meaning the largest exponent in the denominator, is m. And these two things help us develop our three rules for finding horizontal asymptotes. Number one, if the largest exponent in the numerator is bigger than the largest exponent in the denominator, then there is no horizontal asymptote. What's going on is the ends are approaching either positive or negative infinity. We will deal with a special case at some point where we have slant asymptotes, and slant asymptotes only occur when n is larger than m and when n is 1 larger than m. Number two, if n is less than m, then what we have here is the numerator is smaller than the denominator, and as x is going to infinity or negative infinity, the denominator is getting ridiculously huge while the numerator is still getting pretty huge but just not as big, and therefore our horizontal asymptote winds up being y equals 0, the line y equals 0. The last one, if n is equal to m, then our horizontal asymptote is going to once again be based on as x goes to infinity or negative infinity. And since the exponents are going to be the same, the x to n and x to the m wind up almost sort of canceling each other out as x is going to infinity or negative infinity, and the only thing that becomes relevant are the coefficients. So the horizontal asymptote in case 3 is y equals a over b. Going back to our example, y equals 3x minus 6 over x plus 2, you notice that the exponents on both of the numerator and denominator are 1, which means they're the same. So our horizontal asymptote is the line y equals, and then it's just the front coefficients on both, where the coefficient in the denominator is just 1. So our horizontal asymptote is y equals 3. Now, putting together all the information we've gathered so far, we have a vertical asymptote at negative 2, a horizontal asymptote at 3, we have our point 2 comma 0, and our point 0 comma negative 3. We are almost there. We almost have the full graph. There's only one other thing that we have to do in this specific scenario to help us draw a better and perfect graph. Step 5, which is good for graphing anything, is really important when we have vertical asymptotes, because if you remember the graph that we just had, we have a lot of information, but really we only have half of a graph. When we have vertical asymptotes, our best option is to plot a couple more points, especially if we don't know what's going on. But really, for this, the strategy is to try to have at least 2 points plotted on either side of the vertical asymptote. If there's more than one vertical asymptote, we'll have to plot a couple more points. In this example that we have, we only have one vertical asymptote, which means we only need 2 on each side. We actually already have 2 on the right hand side, so on the left hand side we're going to take our example and just plot 2 more points so we can get a better idea of what's going on. My recommendation is to pick some fairly easy ones, especially if you do not have a calculator. So let's see what's going on with negative 4 and negative 3. You'll see if we plug in negative 4 and negative 3 into our function, we get a y value of 9 and 15 consecutively. So looking at my graph, I might want to do another one to plot these points so that I can take care of things. So if I have my graph over here at negative 2, vertical asymptote, 3, I have my positive horizontal asymptote. I have have my x-intercept, my y-intercept, and now I'm just going to quick take care of the other 2 points I found. 4, 5, 6, 7, 8, 9 at -4. And bigger, 10, 11, 12, 13, 14, let's fit it, 15, all the way up there. If you understand the meaning of asymptotes, then you also understand that our graph has to approach the asymptotes. So as I draw through those coordinates I have plotted, I want to make sure that my function is approaching my vertical asymptote and my horizontal asymptote in both directions. This graph, this function that we've drawn and taken care of, is what we call a hyperbola. And that's because it has these 2 branches that we've drawn here, and because those 2 branches are approaching the vertical and horizontal asymptotes.